Hello, my name is Fouad Faraj. I'm a Master of Applied Science candidate at Queen's University in Kingston, Ontario, Canada. And today I'll be going through a video tutorial on spatial data analysis, specifically on cell declustering. So just to give a bit of an outline, we're going to start by discussing why do we need declustering when conducting spatial data analyses. Then we're going to go into a background on cell declustering, and we're going to wrap up with a hands-on Python tutorial for declustering a spatial data set. And this will be applied on a synthetic environmental data set with a real-world application. All right, so why do we need declustering? Basically, it's because of bias or preferential sampling. So generally, regardless of the industry, whenever samples are taken from the Earth in 2 or 3D, generally whenever an anomalously high or low sample is found, more samples will be taken around that because those anomalous areas are areas of interest, and we want to better delineate these. And unfortunately, this bias sampling will lead to a bias in our statistics afterwards. So we have to somehow correct for this. To sort of illustrate that point, here we have 4 diagrams. To the left, we have the ground truth. So 1/4 of this region is made up by this red tile. Samples taken from this red tile will have a value of 5, whereas samples from the blue tile will have a value of 1. Because the red tile is 1/4 of the total site, the true mean for this synthetic site would just be 2. If we were to regularly sample, so if our samples were evenly spaced, then our sampled mean would be the same as our true mean. If we randomize sampling, assuming we have enough samples, we're also going to observe that the sampled mean is equal to the true mean. But when we have bias sampling, so in this example, more samples are taken from this anomalously high zone, will it lead to a bias? So the sampled mean here would be 3.5, whereas the true mean is 2. So there's a difference of 1.5, and this could be quite significant depending on the application. So to correct for this, we implement declustering. Although there are many different types of declustering, here we're going to discuss cell declustering. So what basically cell declustering is we divide up our region into evenly sized cells, and then we assign a weight to the samples in those cells, which is proportionate to the area they represent. And it'll depend on how many samples occupy that cell. So in this simple example here, to the bottom right, we have 1 sample representing this entire cell. So that 1 sample will have the highest declustering weight of 4. To the top right, we have 4 samples representing that same amount of area. So these will all have a declustering weight of 1. And to the left here, we have 9 samples covering a single cell. So these will have the smallest declustering weight, in this case about 0.4. And basically, what the declustering weight is whatever the value of this sample is, we would count it 4 times. So this sample at the bottom right had a value of 5. We would pretend, well, our declustered data set would have 4 samples of value 5. And that's how the declustering weight works. Unfortunately, to run cell declustering, there are a couple parameters we have to sort of understand because they're required as inputs. The most obvious one would be the cell size. So essentially, we have to pick an adequate cell size. So in this example here, we're showing a few extreme cases. To the left, we have the case where we choose the smallest cell size. And in this case, each cell will be composed of just 1 sample. So therefore, all of our samples will receive the same weight. Alternatively, if we use the largest cell size possible, so just 1 huge cell covering all our samples, these will all receive the same weight as well. And neither of these are very helpful for us. We have to choose an adequate cell size, and the adequate cell size will generally be one which maximizes or minimizes the declustered mean of our data compared to the naive mean of our data. So the naive mean would be just the mean of our data, and the declustered mean would be the mean after incorporating the declustering weights. So more on the naive and declustered mean. Here on the y-axis, we're measuring what the declustered mean is for various cell sizes in the x-axis. So all the way to the left here, we have the smallest cell size, and to the right, we have the largest cell size. So at the smallest cell size, all samples are weighted equally, and our naive mean will be the same as our declustered mean. But all the way to the right, at the largest cell size, we get the same effect. So our declustered mean will just be equal to the naive mean because we have basically 1 huge cell covering all the samples, giving them equal weight. But as we increase from the smallest to the largest, so as we get to this adequate cell size, which will either minimize or maximize the declustered mean, that would be our adequate cell size in this example, or somewhere there, somewhere close to this value. So basically, if our biased samples are smaller than the naive mean, as we decluster, our declustered mean increases. This is because all those clusters of low values are receiving a smaller weight, and the clusters of high values are receiving a larger weight, which increases the mean. So eventually we'll hit a maximum declustered mean, or if the cases where our biased samples are greater than the naive mean, as we decluster there, it'll drop down to a minimum declustered mean. And one approach would be to choose our cell size. We could just choose whatever maximizes or minimizes our declustered mean. But there are also other ways of doing so, depending on your data set and application. The other parameter is the number of cell offsets. So as you'd imagine, depending on where we place that grid of cells, we can end up with more or less samples in each cell. So the way we get around this is we use various random origins for that cell grid, and then we just average our results. So in the figure to the left here, we're just showing an example where we're using 3 different cell origins, and to the right we're showing 9. But generally in practice, I've seen 25, 50, or even 100 random origins used for cell declustering. Really depends on the data set. All right, so we're going to use this synthetic data set for our example here. It's an arsenic contaminant data set. So these are various surface water samples taken in 2D space throughout 1,000 meters of easting and northing. There's about 153 samples here, and they're all measuring arsenic concentration in micrograms per liter. So our problem here is that the World Health Organization, or the WHO, they have guidelines which state that the drinking water should not exceed arsenic concentrations of 10 micrograms per liter. But if we were to just take the mean of all our 150 samples, we'd get a mean arsenic concentration of 12.60 micrograms per liter, which is above the WHO guidelines. But now we have to ask ourselves, is this accurate, or is this just an artifact of the clear bias and preferential sampling you can see? So there's a cluster at the top left and at the bottom right, and both of these clusters of data points have anomalously high arsenic concentration. So if we decluster this mean, maybe we'd be below that limit. We'll see. So now we're going to go into a Python tutorial. We are going to need a special Python library, so we're going to have to pip install geostats.py, and then we'll also be using pandas, which is just a standard library in Python. So I'm doing this in Python. Well, first we can install the library we need, so we can just write out pip install geostats.py. I already have it installed here, but it should just take a few seconds to install for you. And after we have that, we can just open Python. Here I'm using Spider. We import our library, so geostats.py. I'm importing it as geostat. And we're also going to be using pandas. I have matplotlib and numpy here for some data visualization, but I already have the graphs made in the PowerPoint. So it's a very simple, declustering is actually quite easy to do because of these libraries. So first off, we just have to load up our data frame. So there's the data set. There will be a link to the script and to the data set in the article, and the link to that article can be seen somewhere in the description below if you're interested. So the important part here is that we have these 3 variables, W, C size, and D mean. So W will just be the weights assigned to each sample. C size would be all the tested cell sizes, and D mean are all the declustered means for each one of the cell sizes. So going through one by one, we'll be inputting our data frame. The column headers for each column in our data frame. So we have east, north, and arsenic. This would just be the eastern coordinate, northern coordinate, and the arsenic concentration. And then here are our actual inputs. So I, min, max will essentially choose which cell size we use. So if we set this equal to 1, it will choose the cell size which decreases, it'll use the cell size that minimizes the declustered mean. If we set it to 0, it'll use the cell size that maximizes the declustered mean. And off, that's the number of offsets. Here we're using 25. You can go ahead and use 50 or 100. That'll just take slightly longer to run. End cell is the number of cells to test. So here we're using 200. And these will be linearly interpolated from the minimum cell size C min to the maximum cell size C max. So we're going from 1 meter to 750 meters. And I know this is in meters because our data, our easting and northing here, are all in meters. So we can just run this really quick, see what we get. So yep, there's 153 samples and just some basic statistics on it. So our data frame it's just east coordinates, northern coordinates, and the variable of interest, which in this case is arsenic. And after running this, so this C size will be, this is all the tested cell sizes, which was just interpolated from 1 to 750. And D mean, these are all our declustered means. And W, these are all our weights. So this is, and they're in order. So all 153 of these weights, each one of these would be basically assigned to each one of the samples in our data frame. So you can almost imagine if we put this in our data frame, it would just be a fourth column of weights. And that's how we could incorporate the declustering weights to our data. Okay. So on cell size selection here, we've plotted the output cell sizes. So from 0 to 750. And so this is cell size on the x-axis and the declustered mean arsenic concentration on the y-axis. And because we had the biased samples, the clusters were all anomalously high. As we decluster these, obviously as we see, the mean drops. So this blue line represents the naive mean. So that's just the mean of our data without declustering. And each one of these black dots is one of the tested cell sizes. And this orange line is the minimizing cell size. So it's the cell size that minimizes the declustered mean. So when the final declustering run will be done with this cell size of about 125 meters, because this gives us the smallest declustered mean. Taking a look at our declustering weights, so to the left we have the data set we showed before, and to the right we're plotting it with the declustering weights we just got. And as you can see, it makes perfect intuitive sense. The two clusters we've had in our data all receive lower weights, around 0.5 to 0.4, or just maybe a little less, because they represent the same amount of area that other samples represent, but there's a lot more samples here, obviously. So these two clusters receive smaller declustering weights. And the samples that are in the outskirts or representing larger areas, like these in the corners, they all receive higher declustering weights because they represent a larger area of our entire site. So very intuitive, makes good sense, makes perfect sense, basically, what we're seeing. So now we're able to achieve more representative statistics by implementing these declustering weights. So here we're comparing two histograms. So to the left we have the naive arsenic, and we see a lot of samples with high arsenic concentrations. And to the right we have the declustered arsenic. So obviously we have much more of the low. You have much more of the low samples now because they all receive higher declustering weights, so they appear more times in our data set. And this better matches what's probably really going on in the site because we've corrected for the biased sampling, which is completely missed in the naive arsenic histogram. So tying it back to our real environmental application, the WHO guidelines states that drinking water should not exceed 10 micrograms per liter of arsenic. And taking a look at this table here, our naive mean for arsenic concentration is 12.60, which is above the limit, but the decluster mean is 8.82, which is below the limit. So if someone was analyzing this data set and they just took the mean of the data, they would report to the WHO that it exceeds their guidelines and that some sort of expensive remediation would need to take place. But if we took into account the biased sampling and we declustered our data set, we'd actually discover that the region is actually fine. The arsenic concentration is only 8.8 micrograms per liter. Another interesting thing to note is that the actual value of our data point isn't changing, which is why we have the same minimum and maximum. So if a sample receives a weight of 2 and the sample value is 5, we're not saying there's a sample now of a value of 10. What we're saying is there are two samples which both have a value of 5. So the weights you can think of as how many times that sample appears in our data set. So you have to be very careful when incorporating that into your statistics. So yeah, the main differences between the declustered and the naive data would be seen in the quartiles and the mean, but the min and max won't show any difference. Anyways, that's it. Hope you enjoyed the video tutorial, and I highly recommend you read the article because it has a bit more information on it. The link to the article should be somewhere below. Thank you.